Hello, everyone. I'm Stephen Hardy, Editorial Director and Associate Publisher of Lightwave, and it's my pleasure to welcome you to today's Lightwave webcast, in which we'll discuss strategies for scaling up the photonic integrated circuit industry with optimized test methods. Our webinar today is sponsored by Keysight Technologies and FormFactor, whom we thank for the help in making today's event possible. Photonic integrated circuits, or PICs as they're often known, have become a common building block for optical modules. Of course, with speeds increasing and power consumption goals shrinking, more stress is being placed on PIC designs than ever before. And this, of course, heightens the importance of proper test strategies and practices when using photonic circuits. Today, we'll look at the evolving world of photonic integrated circuits and as well as strategies for proper evaluation of their performance. It will be my pleasure to moderate a pair of presentations on these subjects. Our first will come from Doug Bainey, Department Manager at Keysight Laboratories. Dr. Bainey has been in the field of microwaves and photonics for the last 35 years. He worked as an R&D millimeter wave engineer in Hewlett-Packard's Signal Analysis Division and later transferred to HP Laboratories, then Agilent Laboratories, and now Keysight Laboratories, where he conducted research in the areas of optical amplifier gain, optical noise figure, and spectral hole burning, and upconversion ZB-LAN fiber lasers. Many of the optical amplifier test methods he developed are in use globally for production test of optical amplifiers. Other research he's performed or directed includes work on Faraday effect optical devices, optical reflectometry, optical coherent reception, and advanced modulation format optical constellation measurement. Doug will be providing an overview of photonic integrated circuits as well as test setups and strategies. We'll also hear from Joe Frankel, Systems Engineer at FormFactor Cascade Microtech. Joe hails from the Pacific Northwest and holds a bachelor's degree in mechanical engineering from the University of Idaho and a master's degree in automation and mechatronics from the Georgia Institute of Technology. Prior to joining FormFactor Cascade Microtech, Joe worked as a systems and motion control engineer at Electro Scientific Industries from 2004 to 2014, designing, building, and controlling high-speed laser processing systems serving the semiconductor, flat panel, and consumer electronics industries. Since joining FormFactor in 2014, Joe has functioned as a systems engineer with a focus on probe station automation. And Joe will leverage that background in his presentation, which will focus on integrated wafer level probing of photonic integrated circuits. Now, before I turn things over to Doug and Joe, I'd like to review our webcast setup for those of you who haven't joined us in a while or are here for the first time. I'll start with the Q&A submission box, which you should see next to the slide area. We invite you to feel free to use this tool to ask questions at any time during the event today. To submit a question, all you have to do is click in the box, type in your question, and hit the submission button. We promise to get to as many of your questions as we can after Doug and Joe finish their presentations. As usual, we don't plan to reveal the names of anyone whose questions we answered today, so you'll be able to participate in the Q&A anonymously if that's important to you or your company. Now, in the event you run into a technical problem during the presentation, you can call for help via the Q&A tool as well. Just describe your problem, hit the question submission button, and Sarah, who is today's webcast technician, will be happy to help you out. Next, if you know of someone who might benefit from seeing this webcast as well, or you just want to revisit the presentation yourself, this event will be available on demand from our webcast archive for the next 6 months. We'll send you an email with a link to the archive sometime in the next day or so, and the archive version of the webcast will also be accessible from the webcast archive section of our website, which you can reach via our homepage at www.lightwaveonline.com. Just look for the word webcast above the navigation bar, click on it, and you'll see a list of all of our webcasts, including this one. We also will be providing copies of the slides if you're interested. If you want to download them, just look for the Event Resources tab that you should see on your screen near the Q&A box. Just click on the tab and you should see the files in there that you can download. And with that, let's begin. As I mentioned, our first speaker is Doug Bainey, who is a department manager at Keysight Laboratories. Doug, take it away.
Thank you, Stephen. and welcome everyone to this webcast entitled Scaling Up the Photonic Integrated Circuits Industry with Optimized Test Methods. I'm Doug Bainey, and I'm pleased to be with you today. The agenda we'll cover today is shown here. I'll provide some motivation for the topic, some basics of photonic ICs, as well as some example chip applications. Then I'll focus on an overview of ways to test the performance of photonic ICs with techniques useful for wafer form. Joe Frankel with FormFactor will address the important topic of how to optically connect to the wafers so that we can test it. Photonic ICs will broadly impact the global economy, including pervasive application of communications where increased density at lower cost drives integration. A communications example is shown over on the right for an IMEC transceiver presented at the 2017 Optical Fiber Communications Conference. There, they reported 896 gigabits per second through a single photonic IC. Other applications include compact laser sensors for automobiles. An example is the UCSB LiDAR PIC on the middle right that is able to rapidly scan an optical beam emitted by the chip in 2 dimensions as shown. This was accomplished by integrating on-chip tunable lasers, gratings, and phase shifters. Photonic ICs may also be applied to chemical and biological sensor applications as well, owing to the high finesse resonators as shown in the lower right-hand image. The integrated optical ring filter resonance frequency is altered by interaction with the biological sample's refractive index. By measuring the resonant frequency shift, measurement of the biological sample is obtained. Perhaps the biggest driver for photonic ICs will be the data centers. They continue to experience tremendous ongoing growth, with data growth at between 20 and 40% per year, and that puts huge demand on the computation, storage, and communication networks. This 2017 OFC plenary slide by Google shows how they've had to scale their infrastructure by 100 times over the past 10 years to handle demand. Then you add in Facebook, Amazon, and others, and the volume is just huge. I read this morning from Light County, and they reported that shipments of 100 gigabit Ethernet transceivers in Q2 17 more than doubled in volume from the previous quarter, and the demand from mega data centers has exceeded their expectations by 10% so far. All this drives data density and cost dissipation or cost reduction, which points to more photonic integration. The photonics industry, I also refer to as the PIC industry, is rapidly changing and growing. Photonic ICs are now part of revenue-generating streams for short links, long-haul links, where PICs are applied to like active optical cables and to coherent optical receivers, and to integrated arrays of transmitters and receivers. When data center optics migrate fully to PICs, there will be a huge uptick in PIC volumes. The general PIC industry will be a heterogeneous one, ranging from pure indium phosphide photonic ICs to heterogeneous mixes of material systems to pure silicon photonics. The overall market will also be a mix of discrete and integrated devices. As PIC applications take hold, so does the end-to-end photonic ecosystem. There's now a viable set of foundries in Europe, US, and Asia, and the growing capabilities offered by photonic design tool people and test suppliers completes the ecosystem. An example of the densities with photonic ICs is shown here, where a 2.54 terabit per second WDM-tuned network was realized by UCSB researchers. This photonic IC included 48 lasers, 93 modulators, and 67 photodiodes in addition to 120 passive elements. The inset shows the PIC relative to a $quarter coin. This chip is further evidence of the tremendous advances in photonic ICs. The fundamental component of photonic ICs is the waveguide that connects the on-chip components to make an integrated device. Taking Maxwell's equations, which I wrote in the upper left, and two more dielectrics, guided light is predicted. The simplest arrangement consists of a higher refractive index core surrounded by a lower index cladding, as shown in the upper right. Let's take a generic look at three popular photonic IC platforms. There's others that I note down below, like gallium arsenide, InGaAs, lithium niobate, and silica, PLC. I'll just look at these three now. Starting with silicon photonics, and that should be SIPH, and it's not silicon phosphide, silicon photonics, written under that view there on the left. This platform advantageously leverages industry's low-cost CMOS platform. Due to the large delta N, the index, between the core and cladding, we're able to make very, very tight bends. In this case, you can see an R minimum of about 10 microns under there. So this allows very compact structures. The platform allows for photodiodes and modulators, but there's no electrically pumped lasers. And that's because there is no direct band gap. Now we look at indium phosphide in the middle there. It also is capable of fairly tight corners, somewhere in the range of 20 to 200 microns, depending on how deep you cut that rib in the guide there. But it has a direct band gap, and so you're also able to get lasers out of the structure, optical amplifiers, in addition to photodetectors and modulators. This, of course, doesn't leverage as much the large-scale platforms, and so I'll talk a little bit about the heterogeneous combinations. On the right there is the silicon nitride. That offers the lowest loss platform, and there you have turning radiuses on the guide, on the photonic IC, somewhere between 1 and 10 millimeters typically. And so this platform is great for sensors and things where you need really high Q, high finesse circuits, and you're willing to take a little bit larger structures for the size of the bends. Now that we have waveguides, we can visualize the modal propagation down these guides. Here we use EM Pro 3D modeling for the simulations. The guides typically support transverse electric, or TE modes, and transverse magnetic, or TM modes, though they may have been designed for just one mode, and the other mode may behave poorly. In the plots here, I guess the movies here, the TM mode is shown in the upper left simulation. Even though it is referred to as a transverse electric mode, you can see longitudinal components of the electric field there. The TE magnetic field is shown in the upper right. It's vertical, and it rolls over the vertical plane as light propagates down the waveguide. The lower windows show the TM electric and TM magnetic fields respectively on the left and right. As can be seen with the dispersed electric field in the vertical direction, any metal on top of the guide will interact with the field, causing increased loss for the TM mode. So it acts as a polarizer. With the modal properties understood, various on-chip optical components can be designed. For example, silicon photonics. Some of the various options are shown there, like wire guide in the picture on the left there, deep rib structures, as indicated. And so with these various guide structures and so forth, then we go on to make the components that are shown on the right on chip. You can make grating couplers, splitters, delay lines. In some cases, those delay lines can be meters long. Rings, waveguide grating routers, photodetectors, and lasers. And so we have a whole set of options there, components that we can put on a wafer. For the case where you need to mix both lasers and passive components, we'll see indium phosphide brought in, or other 3,5 materials, that allow us then to get these active devices like lasers on chip. And that's been done with wafer bonding or with quantum dot regrowth, and also with interposers that can be used to bring in close those active components. With the physics and library components understood in detail, design goes to layout. Then a file called a graphical database system information exchange file is sent to the foundry. In this case, IME as an example. The file contains the information, geometric information, and other information that the foundry needs to fabricate a photonic integrated circuit. After review by the foundry, it will be processed and wafers are then delivered. Testing on your design really starts in the fab, where optical and electronic tests are performed by the foundry during wafer processing to ensure process health. With completion of the process, the wafer is available to test good guy and bad guy. Given the rising investment with each step, especially with the packaging step, and that investment might be 90% of the cost, is essential to test and catch defects early because the cost goes up so much. And it's noted that devices, even early on, can pass DC tests and yet fail RF and or optical testing. With photonic ICs, we introduce a new level of test complexity. There are now more ports, optical ports, in addition to DC and RF, as illustrated on the right-hand side of the image there. With optics, you have issues of polarization alignment to the chip and mode matching to get light into the chip. Inside the chip, you can get polarization mixing at bends that might exist on chip, or polarization rotations due to structural asymmetries, and that can affect performance and thus needs testing. Even though it's called a photonic IC, there may be a lot of electrical connections too, as required for a bias and tuning, so probing can get complicated. An example is a LiDAR chip I mentioned earlier with the multiple electrical connections that are necessary, shown on the lower right. We'll now move into testing, where I'll discuss some of the basics of stimulus response testing in both wavelength and frequency domains. Some questions that one might ask are, well, what laser should I use? What can I do to speed up the test of the wafer that I'm testing? How do I deal with polarization? What if I have a deep dynamic range filter? What do I do? I heard scrambling is good for PDL measurements. Is that what I should do? How do you measure photodetectors and lasers? So these are some of the topics that I'll address. Since the laser is a fundamental tool for providing stimulus, it should be noted that there are a variety of lasers available with different capabilities, and I'll discuss that a little bit here. There's continuous sweep lasers that cover a broad wavelength range, and also they can sweep blazingly fast. In some cases, 200 nanometers per second, or that would be 25,000 gigahertz per second. And it can tune over small ranges, like 3 sweeps per second. So it's quasi real time. Some operate bidirectionally, where as you sweep forward in wavelength, you make a measurement, but also on the retrace sweep, you can also make a measurement because the quality is high and it's designed for that operation in the retrace. Low SFT lasers exist. I'll talk more about that later, as well as what that means. Higher output is handy. In this case, you get outputs up to 18 dBm or 63 milliwatts. And this is particularly helpful for wafer probing, where the initial coupling loss to the surface grating may be high. Other lasers, such as DFE lasers or Fabry-Pro lasers, are also available when fixed wavelength test is required. Insertion loss is perhaps the most essential measurement for photonic ICs. This measurement characterizes a waveguide loss and the loss of various on-chip components such as couplers, filters, and demultiplexers and amplifiers. You can see the insertion loss measurement set up here on the right. The photonics application suite runs the test and controls the tunable laser shown in the diagram. It is then fed to the device under test that I represent with a little DUT in the blue box. Transmitted power from the DUT then goes to the power meter to make the measurements. With this setup, you get very high spectral resolution on the order of a picometer, which is about 125 megahertz. It also offers the 63 milliwatts of laser power in the O band and high repetition rates that increases your throughput and drives down cost. I'd like to note that a good practice with optical test systems is to reduce the number of optical cable connections and keep fiber length as short as possible. This is particularly important with polarization maintaining fiber due to cross-coupling effects you can get at each connection, and that can cause measurement instability due to interferometric effects. Cleanup polarization splitters may be used, but attention must be paid to power calibration and drift following the beam splitter. Sometimes, with high dynamic range, especially when measuring filters, SSE can limit the measurement. Well, what is SSE? Well, it's a source spontaneous emission, an unwanted broadband optical emission associated with the gain used in the laser. Different lasers have different levels of SSE. Since the SSE is broadband, it can get past the filter even though the narrow laser line is rejected by the filter. So the measurements are limited by this noise. So if you're looking for high dynamic range, say more than 60 dB, you need low SSE lasers. You can see in the lower left a filter made with a standard tunable laser and one made with the low SSE shown by the red curve. We get more than 40 dB extra dynamic range with using the low SSE. In this case, the laser is an 81606. On the right, we have a notch filter where there's a lot of out-of-band SSE that can get through. And I get straight through the power meter, even though the laser line is rejected by the deep notch. This also leads to dynamic range, and as you can see in the red curve, it's limited. So that's because the power meter is swamped by SSE. By using a low SSE source, we can gain about 25 dB in measurement range, and that's shown by the green curve there. So we get better, more accurate measurement of the filter rejection. Now I'll show some examples, some additional examples of dynamic range that's achieved during the measurement. And so in the figure on the left is the demultiplexer result showing 4 superimposed channel outputs where we see over 85 dB of dynamic range. On the right is a really deep notch filter where 71 dB of dynamic range is demonstrated using a low SSE laser. And that's a pretty good result. So let's talk about polarization. A critical aspect of photonic circuits is the polarization. They tend to operate in a preferred polarization state, and there's various effects that can distort the preferred polarization state into the PIC, as well as internal factors I mentioned earlier that can rotate polarization. Light polarization states are often visualized using a Poincare sphere, where the position on the sphere indicates where the light is circularly or elliptically or linearly polarized. Optical states are on opposite sides of the sphere. Light with low degree of polarization, such as direct sunlight or the SSE I mentioned earlier, the source spontaneous emission, or the spontaneous emission from an Urbino fiber amplifier, would be represented as a dot in the center of the sphere. Light with 100% degree of polarization is mapped to the surface. By splitting the light onto a polarization analyzer, as shown in the lower left, the polarization light is then determined and plotted on the sphere on the right. Often, as wavelength changes and polarization state will change, it appears as arcs or trajectories on the surface of the sphere, as shown in the lower right. Polarization-dependent loss describes the maximum change in insertion loss of a device over all states of polarization. It is a critical performance metric for PIC designs that aim for polarization-independent operation, or for PICs that have polarization-diverse operation. For single polarization PICs, it is also important, as the launched light can often have limited polarization extinction ratios, and thus two polarizations are actually launched when only one was intended. There are two primary methods of measuring PDL. The first I'll talk about here is called the random polarization scanning technique, or all states method. If one were asked, how can I know the total change in loss over all states of polarization, one might answer, measure all states and record those measurements. And this is the basic idea of the technique. So you start with a polarized laser source, and then you route it to the dot. From the dot, then, you have the power meter, and then you record a plot like shown in the lower right, where you're basically measuring the power relative to calibration. It's a fairly accurate measurement. It takes about 3 seconds of measurement time, typically per wavelength, when you're at about a 10th dB, when you're at small PDLs. And so it's really best for looking at just a few wavelengths. So I'll move on now to another technique, which is aimed at faster measurements. The second PDL method is called the Mueller Matrix method, and it's shown here. It offers very fast measurement. It allows measurements over thousands of wavelengths that would not be practical with the all states method, where you're kind of searching around on the Poincare sphere. The method requires only 4 states of polarization as a stimulus, and as you can see in the figure, that then is routed from the synthesizer, the polarization controller, to the DUT and then to the power meter. That polarization synthesizer generates a state, and it's typically composed of an equivalent of a linear polarizer, quarter wavelength retarder plate, and a half wave retarder plate, and those are then rotated and adjusted to generate the 4 states that we're after. With some math shown there, you get Tmax and Tmin is calculated from that matrix, and then the logarithm of the maximum transmission yields the PDL. And so from that, you get what you're after. This is a fast method because we're only measuring a discrete number of states as opposed to searching the sphere. So over a large wavelength range, you can make measurements in minutes rather than hours for this technique. The setup for the Mueller matrix method is shown here. It consists of basically a tunable laser, the synthesizer, of course the DUT, the power meter, and the controlling software. The Mueller matrix method then is used. Now in this case, Keysight is using 6 polarization states instead of 4, and that gives us actually better results for the algorithms we use. The light from the synthesizer then goes on with the 6 states. The power meter makes the measurements. And then the result then is then calculated for the DUT. The fact that this is fast makes this method more robust against environmental effects. So when you have effects adjusting the fiber, if you have a slow measurement system, that can affect your measurements and result in more measurement error. And as I pointed out, the big advantage of this method is the lack of need to search through that on that Poincare sphere for different polarization states. Just takes 6 states, you get the PDL, and also provides TE and TM analysis directly, all without the need for special polarization alignment at the wafer. What I'd like to show next is an example measurement of the photonic application suite based on the Mueller matrix. And so what we have on the curves here and the upper curves is a measurement from 1285 nanometers to 1320 nanometers. The PDL of this measurement is viewed in the lower plot. The particular multiplexer, in this case, shows a maximum PDL of about 1/10 dB, and the best PDL is on the long wavelength side, as you can see on the lower plot. An additional note I'd like to make is that the Mueller method achieves excellent results for a wide range of PDLs from about 1/10 dB to about 10 or 20 dB, but the uncertainty does rise as you get to higher PDLs. In this case, if you had a really high PDL, you may want to use the minimum maximum transmission methods with a polarization controller at a single wavelength. And that can measure PDL in the 30 or 40 dB range, and that's supported by the software. So let's look now at swept wavelength photodetector test. Here the DUT is a receiver optical subassembly, or ROSA, and you can see from the figure that the test setup is similar to the swept PDL measurement, but with the optical power meter replaced with an SMU, as shown by the green box in the diagram in the upper right. The B2900 source measurement unit, or SMU, measures the electrical output of the photodetector shown in the lower right, and then the software displays the wavelength-dependent responsivity, including individual TE and TM responses. You can also get common mode rejection from these ports and photodetector dark current. So next I show a picture, and that shows the measurement results for this case. The measurements were made from 1290 nanometers to 1350, and actually you can see the responsivity as shown on the plot there. There may be a little bit of delay in seeing some of these images, so I apologize for that. So now I'd like to go to the important topic of optoelectronic measurement. Photonic ICs often contain elements that have a frequency response in addition to the wavelength characteristics. Photodetectors, lasers, they can receive and generate microwave electrical signals, so we need to test that capability. So the Lightwave component analyzer is a powerful tool for doing this, as it can make frequency response of optoelectronic devices. And so what I show here, if you look at the upper diagram, is various modes, actually the 4 diagrams, you see various modes the LCA will operate in. The upper one shows hooked up for measuring just S parameters. The lower left, you can see that there's a broadband modulator that will modulate the source, feed it to your device under test, and get the electrical output. That's great for photodetectors. And then lower right, you have the means to measure modulators, where you can take the source and then feed it directly in the modulator and then run it to the detector. So this provides a comprehensive suite of measurements. And now let's go take a look at the actual test setup. Here's an example setup for LCA measurement of a photodetector frequency response. Modulated light to 60 gigahertz in this case is ported through from the LCA to the wafer, as shown by the lower red path, and that feeds the optical probe. A microwave probe then connects the photodetector to the return LCA path, and that's indicated by the blue electrical path. And that carries the photodetector response back. I should point out that in addition to the lasers provided on board, there's also external lasers can also be used for testing other wavelengths other than 1350 nanometers. And Next, we'll show a measurement result from this. In this case, it's a Photodetector Frequency Response measurement shown out to 60 gigahertz. There are actually two responses shown, and I'd like to drive home a point here, is that proper calibration is essential in these measurements. So if you look at the magenta curve, you'll see a fair amount of ripple there where the calibration wasn't done properly, and the cables, the various cables in the system were not removed. But by calibrating, you get a nice smooth response as shown. In this case, we see about 40 gigahertz for this device in terms of 3 dB response. The various test scenarios discussed today are summarized here in this stack of diagrams and solutions I show here. We introduced simple insertion loss, polarization-dependent insertion loss, also polarization-dependent responsivity, as well as measuring optoelectronic devices. But there are more measurements that can be made. Additional tests, such as functional tests, are kind of illustrated here. I won't go through them, but just point out that often as you get the packaged device, you'll also start looking at time domain measurements and so forth. You might look at laser line width, relative intensity noise, and so there are solutions for this, for these types of measurements. So while DC and microwave probing are relatively mature, there is the issue of how do you connect to the wafer. And so this brings up a lot of important aspects such as the angle, spatial position, the coupling, and we actually don't make contact with the wafer, it's standing off. So I'm going to hand it over to Joe with FormFactor, and he's going to describe some of the solutions they have for making these wafer probe measurements. So I hand it over to you, Joe.
All right. Thanks, Doug. That was very interesting stuff. Appreciate the intro. Like you said, my name is Joe Frankel. I'm a systems engineer here at FormFactor in the System Business Unit, formerly known as Cascade Microtech. And I'm here to talk about how to connect to the DUT, or as we say, integrated wafer level photonics probing. Over about the past year or so, I've been working on a team that spans 3 companies on a project to integrate the Keysight measurement equipment with our probers and also some optical positioning systems from PI. At FormFactor, we supply the probe station itself, some of the positioning hardware that brings the fiber down to the DUT. Of course, our standard probe control software for moving your wafer, aligning, handling, and image processing for vision alignment, and a new piece that connects the Keysight and the PI hardware in software to form the whole integrated system. On the right, PI supplies the optical positioners, and they come in a couple different types, and I have a slide to show what those look like. The control systems for the positioners, and then the alignment software. And then the centerpiece there from Keysight is the Photonics Application Suite software combined with the tunable laser and the polarization synthesizers that Doug talked about. And the combination of all of these subsystems working together provides this integrated solution that enables wafer level probing of these silicon devices. So here's a few pictures of our setup in our lab. On the left-hand side, you see, first of all, the CM300XI probe station, which is a standard product of ours, 12-inch wafer prober. It's got material handler if you select that option, vision, XYZ theta motion, and the typical prober alignment algorithms. On the right, 2 pictures, they're the examples of the 2 different types of optical probe positioners that we're supporting for this type of application. And I got another slide to show more on that. And then back on the left and the bottom, you see the tunable laser source that Doug talked about, the polarization synthesizer, which manipulates the output of the laser before it's sent to the DUT. The SMU that provides the bias voltage, or the bias and the measurement for the optical-electrical probing. And then the first power meter that we used that has the sensitivity needed for the measurement. On top of the cart there, you see the optical positioner controller, and this is one of the 2 types that we have. along with the other power meter, which is a log compressed power meter for a wider dynamic range just for the alignment function. And then finally on the top of the stack is this Z displacement sensor driver that I have more to show in the next slide coming up. Here's a little more detail that shows the two different types of optical positioning systems that we're supporting. On the left is the XYZ nano positioning system. So it has 3 degrees of freedom coarse motorized motion over about 25 millimeters in XYZ. And then we can adjust the angle, fiber angle arriving at the grating couplers by changing the fiber holders. Riding on the coarse positioner is the nanocube, or the fine positioner, which has 100 micron of motion, but with very fast servo motion to perform the optical scans. And then on the end of the nanocube, we mount the fiber holder and the fiber itself, and also the Z displacement sensor. On the right-hand side is the hex nano positioning system. So this is parallel kinematic 6 degree of freedom motorized adjustment. So you've got XYZ plus the theta X, theta Y, theta Z. They also have the XYZ nanocube fine positioner mounted on the front of them, and a similar probe arm and fiber holder as well. So you can choose either one of these type of positioners depending on your application needs. This slide shows the details of bringing the fiber down to the work surface. In the top left, you see the dimensions there shown as fiber height and fiber angle. These tend to be important probing parameters for different applications dependent on the design of the waveguide and the PIC. The fiber angle is an important one as it changes with wavelength, and the fiber height we control with this in real time with the Z displacement sensor, providing feedback right at the coupling point so that it can reject any sort of disturbances in the kinematic loop between the wafer and the probe tip. On the bottom right, you see kind of the top-down view you would see in our vision system, and because of the angle and the exposed fiber, you can see the fiber above the coupling points on the wafer for the setup step, and it makes it convenient for this coarse alignment before you initiate an automated test sequence. This slide shows the difference in the alignment setup between an optical to optical measurement as compared to an optical to electrical. In both cases, you have the tunable laser source where the light begins, and then that is manipulated through the polarization synthesizer to set the polarization state at the work surface, or going into the input side. That gets routed through the fiber down to the DUT, and in the optical side, the light comes out the other grating couple on the other side back into another fiber on the output, and then gets converted to an electrical signal in the optical power meter, which feeds the real-time positioning loop for the optical alignment. On the right-hand side is the optical-electrical measurement setup, which is the same on the input, but we replace the output fiber with one of our RF probes connected to the B2901A SMU to provide the biasing and take the electrical measurement. Now, the signal process amplifier in this case is taking that electrical signal and passing it back into the alignment system. So the main differences between the two here is on the left, when you have an optical-optical, there's both cases there is an optical to electrical conversion taking place. In the optical-optical on the left, the optical power meter outside the wafer does that conversion, but on the optical-electrical, that conversion is actually done inside the DUT on the wafer. Now here's a view block diagram illustrating how all of our software applications are stitched together for the integrated solution. The big gray box in the top left represents the PC that runs in our probe station. And when you order a CM300XI, it comes with the Velix probe station software, and which is really a family of applications, each one serving its own purpose. Control center handles the motion control of the wafer, the motorized scope, if you have one, various functions. The spectrum in the center lower there is our vision application, which provides the vision feedback and optical or image processing algorithms. Wafer map on the left is where the position of your DUT, your fiducials, your die size, that kind of information is stored when it's aligned. And then you've got this scripting console, which is a place that it's kind of like a sandbox where you can prototype your test sequences by assembling lists of SCI commands to execute your test sequence. The integration toolkit is the interface to the test executive so that you can develop your scripts in either scripting console or your own test executive. All of the data that passes through Velix goes to the central message server hub. Now in this project, what we've added is a new application called SIP Tools, which bridges the gap between our existing Velix software and these third-party apps such as the Keysight Photonics Application Suite and also the alignment software from PI. With SIP Tools, you can then send scripting message or scripting commands through the message server, and if they're an SIP command, they will get routed appropriately down into those subsystems to provide a single interface to the test executive, so that now you can command all of these subsystems through a single interface. And I really think this is the key to automating everything and enabling a lot higher volume test data with a much less effort than you would by manually hopping back and forth between all these applications. This slide is an example of some of what the optical scans look like. In the XY axis in both cases is the position of the piezo nanocube in XY with the 100 micron range. On the left is a sinusoidal scan, so there's a sinusoidal scan in one axis and then a ramp in the other axis. On the right is a spiral scan where the sinusoid is now in an angular motion and the radius is this sweep axis, and it's a ramp, and so it starts in the center and spirals outward. In both cases, the Z dimension here is the transmitted power through the DUT as received on the far side of the optical power meter. And someone asked the question, why is this peak so wide? Because we know the coupling point is much narrower. I think if you look at the label on the axes, there's something like 30 or 40 micron. And the reason is because this is a signal from a log compressed power meter, so it's got a very wide dynamic range, and you can sense very large and small signals simultaneously. That's also the reason why we need two power meters, because for the actual measurement, we need a narrower range with higher resolution. Now this slide shows, now once you've finished your alignment, the next step is to do your measurement. There's two different examples taken on two different stations and two different measurement engines. The left one being the insertion loss only at a fixed polarization state. And you can see each curve there represents a sweep across different die along one wafer. So, you know, there would be this test sequence that I have a video to illustrate in a minute that shows the wafer would step the fibers from DUT to DUT, do an alignment with the optical scan, and then execute one of these measurement sequences. And then here's all the data from multiple die laid on top of each other. One on the left is from the IL engine. The one on the right was from the PDL as well, so we've got also a varying polarization state at each wavelength as well. The data on the left was taken on a prototype here in Portland, and then the data on the right came from a system that we built in Germany. This slide shows the silicon photonics command set. So for people that may be familiar with test execs and programming probers, in addition to the standard Velix probe commands such as align wafer, step next die, move probe, things like that, the SIP tools adds a new set of commands that are available for test exec programmers to script as needed for their motion sequence or their test sequence. I'm not going to go into details on what all these do, but it just should give you a sense of the commands available based on what they're called. that you can assemble as you need to perform your measurements. So my last slide, I'm going to step over to a video, and I'm going to play a demonstration that illustrates all of these subsystems working together to produce an automated measurement.
This video illustrates integrated wafer-level silicon photonics probing. First, you see SIP tools being launched in slave mode so that it responds to commands sent through the VELEX message server. Then you see the VELEX scripting console launched a script to execute the probing and measurement sequence. As the video runs, in the upper left corner you see the spectrum vision window focused on the input fiber aligned to the input side of a grating coupler. There's also another output fiber at the other end of the waveguide, not shown in the same field of view. At each die, you see the chuck move to the new die, and then the fiber will scan across the grating coupler and measure the transmission as a function of XY position of the piezo crystal. This data is then updated in the 3D graphs in the top right. In the bottom left, you see the real-time measurement of the coupled power through the device, which drops as the fibers move away to step to the next die, and varies slightly as it aligns and then does the measurement. In the bottom right, you see the insertion loss engine in the PAS application suite, measuring the insertion loss as a function of wavelength. At each die, this sequence repeats itself for each die selected in the wafer map.
Okay. And with that, I'll turn it back to you, Doug.
Okay, let me get the slides here. There we go. All right, thanks, Joe. So summarizing the seminar, we reviewed the basics of photonic ICs and gave an overview of testing methods for on-wafer characterization. This included swept methods, polarization, as well as dealing with SFC, deep dynamic range, and presenting methods such as the Mueller Matrix method and the all-states method for polarization measurement. This was followed by the excellent presentation by Joe Frankel from FormFactor, showing how measurement hardware, motion control, and software are all brought together and integrated to create a probing solution. I put some references down at the bottom here in case you want to read up a little bit more about some of the measurement techniques. And on the part of Keysight, I would like to thank Joe Frankel from FormFactor for his excellent presentation, as well as the Lightwave staff and Stephen Hardy for hosting today's webcast. Thank you for your attention. I will now hand it over to Stephen for the Q&A.
Thank you very much, Doug. Indeed, it's time for the Q&A. While we're looking at some of the questions that you folks have asked during the presentation, we'd like to take a minute or two to have you take a really brief 3.5 question survey that'll help us get a better idea of your engagement with the topic, and enable us also to follow up with you on some of your questions as well if we need to. So first, obviously, the question is, please rate your overall satisfaction with this webcast, 1 being poor, 5 being excellent. If you'll just take a moment or two to let us know what you thought of the event. All of these questions are actually going to be on one screen for you. So basically, you can, once you've finished answering that question, you can slide down to the second question, which is, after viewing this webcast, do you have a need for any of the measurement solutions that were discussed? And if you do, please select all that apply. And we'll give you a few seconds to fill that out as well. Once you're done with that one, If you did indicate that you have some interest, if you could let our sponsors know what your time frame is in terms of your interest in the technology. Great. So you folks are doing that as well. And then finally, I believe there is a box that will enable you to add additional comments. So anything either about the technology presented or the topic or the webcast. And then, of course, when you're done, if you could hit the submission button, that would be helpful as well. Very good. So let's see. So we'll just give you a couple more seconds to answer the questions. And again, please hit the submission button when you're done. And with that, let us indeed slide right into the Q&A. If you have a question, as a reminder, all you need to do is type it in the Q&A box, hit the submission button, and it'll join the queue. And it looks like several of you have done that already. So let's start with one for you, Doug, since you are our first speaker. So you talked about insertion loss testing. Here's one on swept IL methods. Will swept IL methodology work for photonic IC amplifiers?
Swept insertion loss for photonic IC amplifiers. That will work, but there are some caveats that need to be paid attention to, because with semiconductor optical amplifiers, the performance depends a lot on the input power. And so you need to be very careful that you understand the input power that's being delivered to the amplifier. In addition to that, once you've got the parameters set straight and the amplifier has gain, of course, you need to pay attention whether amplified spontaneous emission is corrupting the result. But in general, it should be possible to scan an amplifier.
Very good. Again, if you've got a question, now's the time to ask it. Just type it in the submission box and hit the submission button. Joe, here's a question for you. On one of your slides, you were showing pictures of two different setups. One was the XYZ Nano, and the other one was the Hex Nano. Can you talk a little bit about the difference between the two and which applications one might see them being used for?
Yeah, sure. The XYZ Nano has a 3-axis XYZ motor stage and a 3-axis XYZ piezo stage. So then you can adjust your fiber angle by changing out the fiber holder, because we have an array of different designs for that, depending on if you need a 6 to 20 degree fiber angle. The Hex Nano is a parallel kinematic hexapod with 6 degrees of freedom, XYZ, plus the theta is about 3 as well, and that provides motorized motion. Both cases have the piezo cubes mounted to them, so you can perform the fast scans and the optical alignment. But really the difference is, do you need to have a variable angle you get with the hexapods motorized, or would you prefer just to have the XYZ? The main benefit that we see for the Hex Nano is that as we develop fiber array alignment, we think we're going to need some small correction motions in angular corrections as we step around the wafer and align an array of fibers to an array of waveguides.
Very good. Again, if you've got a question, just type it in the Q&A submission box, hit the submission button, and it'll join the queue. Here's one for you, Doug. This came up during the course of the event, and I believe you mentioned it a couple times, but it may have slipped past a couple of people. And that's the definition for the acronym SSE. Could you tell us what that is?
Yes, SSE stands for Source Spontaneous Emission, and it was a term that was defined specifically for test, where the source lasers, in addition to coherent narrow line width, produce the broadband emission, and that broadband optical emission is called source spontaneous emission.
Very good. Let's see. Here's another question for you as well. As far as the polarization-dependent loss measurement is concerned, is calibration required for such PDL measurements?
Yes. In the Mueller Matrix formulation in the slide deck, and I think people could probably go there afterwards, there's a point where there's calibration required to do so. And those power measurements, you want to keep them stable and after calibration so it doesn't upset the total calibration for the Mueller method.
Very good. Let's see. I realize that we're past the top of the hour a little bit, but I see there's also a lot of questions, so we're going to hang in there for another couple of minutes, including to ask this question of you, Joe. So what's the difference between the motor stage and the PCO stage in terms of the setups that you were showing?
Yeah, motor stages have a wide range of motion, both in XYZ nano and hex nano versions. Those are used for coarse alignment over millimeters type of range with a micron level kind of accuracy. The piezo stage that rides on the front of both of those systems is only has 100 micron in XYZ of motion, but it's very fast. So it allows you to do these high frequency scans and capture your transmission measurements as it scans in real time. And it has accuracy on the order of nanometers. And when you combine that with the Z displacement sensor, that gives you very accurate positioning of the fiber over the grating couplers.
Very good. Doug, we'll continue the tennis match here and bounce back to you. Here's a question from somebody in our audience regarding ring resonators. What laser do you recommend for characterizing ring resonators?
Ring resonators are often very narrow in line width, and they're also subject to environmental effects where the filter can actually move with time. And so the lasers that are preferable there would be ones that have very narrow line width and also can tune very rapidly so you can sweep the filter curve rapidly, and also have low SSE so that if it's a notch filter, in the case of the question, you can improve your dynamic range as well as the bandpass filter case. So a low SSE laser with narrow line width that tunes really fast so you can get a nice measurement of the shape of the filter.
Very good. And I think we have time to squeeze in one final question, and this one will go to you, Joe. Let's see. In one of the setups, or several of the setups we've been looking at, we've been looking at the use of 2 optical power meters. Why do you need 2 optical power meters?
Oh, sure. That one, we have 2 needs here. We have 2 functions. One function is the alignment function, and the other is the measurement function. For the alignment function, we need to capture a fairly large dynamic range from, depending on your source setting, your insertion loss, how much light makes it through when you're not coupled or you're slightly off axis and only a little bit is getting through. So we have a log compressed optical power meter that feeds the alignment system. So the voltage applied at the alignment controller is proportional to the log of the power arriving at the optical meter. On the other side, for our measurement, once we're aligned, we don't need such a wide dynamic range, but what we need is much higher resolution. So what we do is we split the output fiber into 2 light paths and then sense them through the 2 different meters, one for the alignment over the wider range and the other for the measurement that's feeding the PAS application suite.
Very good. Thank you. And with that, we've come to the end of our program today. If we didn't get a chance to answer your question just now, and I know there were several of you who asked questions that we didn't get a chance to ask. And you want to contact our speakers directly, you can do so via the email addresses you see here on your screen. Our speakers also have promised to follow up as well. These addresses also might be useful if you are watching the event on demand. Speaking of which, as I mentioned, this session will be archived for future access, which should take place in about the next 24 hours or so. You'll receive an email with a link directly to the archive, and the archived version of the webcast will also be accessible from our homepage, www.lightwaveonline.com. Again, just look for webcasts above the main navigation bar. Click on that, and you'll get a list of all of our webcasts, including this one. If you are looking for a copy of the slides, you can find them under our Event Resources tab, which you should see on your screen. Just click on the tab, and you'll see the files there, and they should be directly downloadable from there. Finally, I'd like to thank Doug and Joe for sharing their expertise, Keysight Technologies and FormFactor for the help in making today's event possible, and of course, you and our audience in particular for attending. I hope you'll join us for our next Lightwave webcast, which will take place on Wednesday, September 27th. I'll be back to moderate a webcast at that time on high-speed networks, which will look at what's new at 100 gigabits per second and above. Until then, enjoy the rest of your week, and goodbye.